Hello and welcome back to another episode of Statistical Wizardry. I am your host, Professor Albus Fife, and today we have a very special guest, as we always do, by the name of Hawk McClagan. Hawk, why don't you introduce yourself? Aye. Is that all you're going to say? Aye. I'm a man of few words. You know, I invited you onto the show so you could talk, right? Of course, you ninny. I'll talk when it's time. Okay. Well, without further ado, let's go ahead and begin. So today we're going to be talking about theory, good science, and validity. And in particular, we're going to be talking about internal and statistical conclusions validity. So first, we will talk about a validity typology, different threats to validity. Also talk about internal validity, what it means, and what those threats to internal validity are, and how we can address those threats. And then we will conclude with statistical conclusions validity. In other words, what does that mean, and what are those threats to statistical conclusions validity, and how can we address those? Aye, validity. It's something we're all concerned about, aren't we? Validity refers to the truthfulness of an inference. If you make an inference, you want to know that it's true. But there are several inferences we may not be able to make. For example, I might infer this medication causes depression to go down in my sample. Here, you're making an inference about internal validity. You're saying that the depression was reduced by the medication. Or perhaps you might say that you infer the treatment group is statistically different from the control, in which case you'd be making statistical conclusions. And your concern might be, are these statistical conclusions valid? And you might never know. Likewise, you might make an inference that these scores on depression accurately measure actual depression. Well, in that case, you're making an inference based on construct validity. And finally, you might infer that what you found in your sample will generalize to some other population, like undergraduate psychology students. What you find in the lab, will it generalize to the population of all people? Likely not. In which case, external validity is threatened. Aye. Correct, yeah, exactly. And so all these forms of validity we're going to be concerned about, and different designs address different sorts of validity. So how do we know whether our conclusions, our inferences, are justified? So when we are talking about validity, we often talk about threats to validity. So the strength of our inference is determined by the degree to which threats influence our validity inferences. So a threat is a reason we might be wrong in making our inference. So we can strengthen the validity by systematically eliminating these threats to validity. Aye, good cartoon there. There's a flaw in your experimental design. Oh, the mice are scorpions. Oh, that's a good one. That's a funny one. So this would be an example where the validity of the experiment is threatened. So let's go ahead and take a break and talk about, and just do a quick mid-lecture quiz. So what type of validity is threatened in the following situations? So let's say Sam wants to know how effective P90X is relative to a control group. Consequently, he goes to a local gym and measures the BMI of a P90X class and compares it to a random sample of couch potatoes. He concludes P90X is effective at increasing weight loss. So what sorts of inferences are Sam making here? So one of them is that he's inferring that the difference between the couch potatoes and the people who do P90X is due to P90X. Well, probably not. there's some self-selection going in here. So the type of person that chooses to do P90X is going to be inherently different than the type of person who chooses to be a couch potato. So it may be that what you're seeing is not P90X, but the person's natural disposition or natural desire to exercise. So, yeah, moving on. So let's say George wants to test whether people like Coca-Cola or Pepsi more. He randomly samples 6 participants and has them taste both. He concludes there's no difference. So what inference is Sam making here? He's inferring that those who drink Coca-Cola versus those who drink Pepsi are no different. And so what are ways that this inference can be threatened? Well, the most obvious way that it can be threatened is that he's only got 6 people. So you're trying to make an inference about everybody based on 6 people? Probably not. And we'll learn later on today that that is a threat to statistical conclusions validity. So when you have a small sample size, it reduces power, it reduces precision, and makes you less able to conclude broad inferences based on that very small subset of people. So that brings us to internal validity. So in our study, we want to make causal inferences, and I am going to be unabashed and unashamed about using the word causal. Judea Pearl noted that in science we are afraid of the word causal and we treat it as a bad word, and we ought not to. And I agree with him. And so I'm going to talk a lot about causation here. So when we're designing a study, we want to make causal inferences. We want to say that the treatment caused people to be less depressed or whatever it is. So our question might be, are these inferences justified? Well, that's an issue of internal validity. So internal validity refers to the strength of these causal inferences, and internal validity always refers to causal statements. Always, always, always. So if I were to ask you, how might internal validity be threatened? Your immediate thought ought to be, how are the causal statements that I am trying to make being threatened in this study? So again, when you think internal, think causal. So what are the threats to internal validity? Well, there's ambiguous temporal precedence. So what that means is we might want to infer that A causes B, but it may be that B causes A. So what comes first? So an example of this might be, you might suggest that people are depressed because they are less socially engaged. And so you are inferring, or you're saying that the cause of depression is social attachment, or whatever I said. So social attachment causes depression, but it may be that it goes the other way around. That if you are more depressed, you have less motivation to go out and make a social connection. And so here would be an example of ambiguous temporal precedence. We don't know whether it's social causing depression, depression causing social, or maybe there's some sort of feedback loop going on there. Another example is selection. So with the P90X example, that was an example of selection. So that was a threat to internal validity. So the observed difference we see is not due to the treatment or whatever variable you're inferring. It is due to pre-existing self-selection. So an example that you might see, they frequently do studies of those who are vegan versus those who eat red meat and try to use that sample to conclude that eating red meat causes cancer or heart disease or whatever. Well, the problem is that vegans tend to be healthier and tend to exercise more and tend to be more conscious of the things that they're eating. They tend to eat more vegetables. Whereas people who eat red meat, well, some of them are like that and some of them aren't. But you're more likely to be a whole lot more healthy if you are a vegan. And so it may not be not eating red meat that causes differences, but it may be some of these other lifestyle characteristics that are causing these differences. So if that is playing a role, then that would affect your ability to make inferences. Another one is history. So history basically says that changes that happen outside of the lab are responsible for the observed difference, not the treatment. Oh, look at that. I think I done messed up here. History. Oh, okay, I see what I'm doing. Okay, so when I made this PowerPoint, I messed up. So, blood pressure reduction, forget about that example. So an example of history might be, let's say you were doing a experiment on, let's see, you were looking at opinions of gun control, for example. And let's say you recruited 20 participants who were liberal, for example, and you asked them their opinions on gun control. And most of them are in favor of very strict gun control because liberals tend to be in favor of gun control. And so now let's say subsequently, after you recruit the 10 liberals, you then recruit 10 conservatives, but in the middle of the experiment between recruiting the liberals and the conservatives, there is a mass shooting that happens that is widely known in the public. And suddenly, these conservatives who would otherwise be less in favor of gun control might say, well, given what just happened, I'm a lot more open to the idea of gun control. And so you might be tempted to conclude that conservatives and liberals, it doesn't make a difference in terms of their desire for gun control, when in reality it's actually what happened outside of the lab or history that threatens that inference. So another example is attrition. So attrition means subject dropout. So if you have subjects drop out of at different rates in the treatment versus the control group, then that's going to threaten your inferences. For example, if you were doing an exercise program and you randomly assign one group to do something very rigorous like P90X and the other group was something much less rigorous like yoga, and you wanted to compare the difference between the two, and of course it is much easier to drop out of P90X than it is to drop out of yoga, or people are more likely to drop out of P90X because it's so rigorous. And so the people who did not do well in P90X or who had little motivation dropped out of the study, and then at the end of the study, unless you do some sort of sophisticated algorithms, you're going to end up comparing those, only the strongest in the P90X group to only the strongest in the yoga group, but only the threshold for strongest is much lower in the yoga group than in the P90X group. And so what you're observing is not differences due to exercise, but differences due to motivation. So all these are what we call confounds. So anytime there is an alternative explanation for the causal inference you are trying to make, we call it a confound. And a confound is a threat to internal validity. And so how do we address those threats? Well, it's actually very, very simple, conceptually at least. The best solution is random assignment. So on average, when you randomly assign people to treatment versus control group, it will equate them. So the highly motivated people will be in the treatment group and in the control group. Then the only difference between the two must be due to the treatment. Now on average that will work, which again highlights the importance of replication and large sample sizes and that sort of thing. However, random assignment does not address attrition and testing, which we haven't talked about today, but we'll talk about later, and some other things, which again we'll get to later. So in summary, we got many different potential ways in which we can confound our results, and the best way to address these is to do random assignment. Anything you want to say, Professor McLagan? Nay, you covered it quite well. But statistical conclusions validity. What is that all about anyway? Say we want to make some sort of statistical conclusion, such as reject the null hypothesis. And so, what this refers to is we want to know, is it valid to make this inference? Is it valid to conclude that the null hypothesis is false. Or vice versa. You might make either conclusions and be wrong. So what are the threats to statistical conclusions validity? Well, perhaps the biggest is low statistical power. For example, if we have a sample size of 5 people in each group, we're probably not going to reject the null. It is not because the null isn't rejectable, but it's because we have such a small sample size. On the other hand, if we increased our sample size, we may have found a difference. And so the conclusion that you make is false. Another threat is violating statistical assumptions, such as the assumption of linearity or homoskedasticity. If you violate these assumptions, well, your inferences will probably be wrong. And likewise, we've talked about this before, if you fish, if you measure a crap ton of variables and do tests on all those variables and only report those that are statistically significant, you're in a large load of trouble there. You might find statistical significance, but it's not because it's really there, but it's because you're playing with the laws of probability. Yeah, exactly. So let's look at an example here. Let's say Tom wants to eliminate faulty eyewitness identification. And he believes that if he has subjects participate in visual meditation before seeing a lineup, it will somehow reduce incorrect identification. So he goes on to a local police station and has 44 actual witnesses attempt to identify criminals. It is known beforehand through DNA testing whether a suspect is guilty or not, and what Tom finds is that his meditative procedures increase the proportion of correct responses for armed robberies. Okay, now it may not be immediately clear how this relates to statistical conclusions validity, but stick with me for a minute. So what conclusion is being made here? Well, Tom is concluding that meditating increases correct responses for armed robberies. Okay? So what threats to validity may be at work? Okay, first of all, we have 44 witnesses, and so that may not be the largest sample size, but typically with smaller sample sizes, we are more likely to make, well, this isn't even true. I'm going to lie to you temporarily until I can talk to you later, but let's just pretend that we are more likely to make a type 2 error than a type 1 error. Well, Tom has actually concluded that, well, he has rejected the null here because he's made a conclusion that there's a relationship between armed robbery identification and meditation. But there's an even bigger issue here. So when I read something like this, and I read something like this all the time where you read a study that says, we found this relationship for this variable under this condition, and under this condition we found this variable. And so my question at that point is, okay, so armed robberies? Why specifically armed robberies? Did you have a theoretical reason for testing just armed robberies? Likely not. I'm guessing what Tom did was he first grouped everybody together and looked at differences between those who meditated and those who didn't for all crimes, found no difference. So then Tom subsequently said, well, maybe it's just murders. Didn't find anything there. Okay, maybe it's just rapes. Didn't find anything there. And then he says, all right, well, let's look at robberies. And then bingo, he finds something. And so when you see these kind of weird conditions going on, hopefully immediately you think, holy cow, there's some phishing going on, or there's some p-hacking going on. So anytime there is a conclusion that seems a little nuanced and that nuance isn't well developed from the theory, then that probably indicates that there's some p-hacking going on. So in this situation, statistical conclusions validity is probably going to be threatened, and it probably has nothing to do with armed robberies and meditation. It's just that you're playing a game of chance at this point. So now that gets me into, this is a presentation I gave at APA in 2018 about what I call the 8 steps of data analysis. And these 8 steps are developed with the intention of eliminating type 1 errors. And so with that, let me begin here. So despite decades upon decades of criticism, I believe the first criticism of NHST began in like the 1930s. And so despite vehement criticism, NHST is still here. Now, why is that? Well, there's social pressures for doing NHST. There's habit. There's also the learning curve. So anytime you try to introduce a new statistical procedure, it's going to require a pretty extensive learning curve. Another thing about p-values is they provide a translational mechanism, as Cortina and Landis noted. What that basically means is it provides an objective map from theory, your introduction section, to data, which is your results section. I believe I talked about this in the very first slide, or very first lecture. And so p-values help reduce ambiguity and provide a map from theory to data. And finally, there are few digestible alternatives, or at least some of those alternatives haven't been well mapped out and developed. And so those are my suspicions on why NHST remains. Now remember, we're talking about this within the context of statistical conclusions validity, because the problem with NHST is that it tends to lead to a whole lot of type 1 errors. And so the 8 steps of data analysis invites researchers to look deeper into what their data are actually telling them. And these 8 steps shift the focus away from significance tests and toward estimation and toward understanding and recognizing uncertainty inherent in data analysis. And finally, it places decision-making, such as what is significant versus not, back in the hands of the scientific community where it actually belongs, rather than in the hands of convention, such as p less than 0.05. So what are the 8 steps of data analysis? Hopefully you've read the paper and you understand what they are, but to summarize, step 1 is to state the theoretical hypothesis and the decision criteria. And this would be done at pre-registration before you even collect data. And as I mentioned in the first lecture, this is tied to specific parameters in a statistical model. We prefer strong hypotheses where we are suggesting exact values rather than saying there is a difference of 0. We might say there's a difference of 0.5 between the treatment and control, or the correlation is 0.3 or higher. And then finally, we set decision criteria that may or may not be based on a p-value. In fact, we'd probably better not to use a p-value. So we might say if the effect size is less than 0.2, I don't care about it. Or if the number of cigarettes smoked per day is not reduced by more than 5, I don't care about it. Those sorts of things. Step 2 is that we assess the psychometrics, and the idea here is that if we improve reliability by a factor of 2, that is equivalent to quadrupling the sample size. Holy cow! So basically you get more bang for your buck by improving reliability. Step 3, we plot univariate distributions, so that's gonna be either histograms or bar charts. You can also use QQ plots or density plots or something like that. But basically, the point of this is we're trying to identify outliers, errors in coding, group imbalances, and nonlinearity. Step 4, we plot a graphic to match the analysis. And the rationale behind this is it directs our focus to the size of the effect, it improves encoding, and helps identify problematic assumptions. And that may be the most important step, is to plot the graphic that matches the analysis. Step 5, we study residuals, and this helps us to identify whether the model chosen is the right model. And step 6, we study the parameter estimates and effect sizes. And by doing that, it encourages us to focus on estimation and also prevents making a mountain out of a molehill. We all hear about those situations where people say that an effect is statistically significant, but the effect is so tiny that really it's not clinically significant, and we don't care about it. In step 7, we make our decision based on what we already specified in step 1. By the way, this is optional. Not all studies require making a decision. And so our decision may be based on Bayesian estimates or NHST significance criteria. I tend to think that that's less important than instead using user-specified criteria. So number of packs a day. If your treatment works and it reduces people by more than 5 packs a day, or reduces smoking by more than 5 packs or cigarettes or whatever I said a day, then we decide for ourselves that that is clinically significant. And so this step 7 translates statistics into theoretically and clinically meaningful conclusions. And then step 8, now I said earlier step 4 was probably the most important, and well, actually step 8 might be the most important, which is to replicate on a new independent sample. And so let me just do an example of this with you. I'm going to very briefly go over this. If you have any questions, we can certainly talk more about this later. And so I just made up a hypothesis based on the NSDUH dataset, which is a national dataset about drug and alcohol use. And so I created a question and said, let's say we want to identify how much healthy behaviors mitigate psychological distress among heroin users. And in the process, let's control for mental illness and the rationale behind that. Now, this was an a priori decision to control for mental illness because we know that mental illness is going to influence healthy behaviors, and we know it's going to influence psychological distress. But what we really want to know is the independent effect of healthy behaviors on distress once we control for mental illness. And so if we were to do a standard NHST analysis, we might conclude self-reported health rating was significantly associated with psychological distress, and then there's our F ratio and our mean squared error. We report a p-value, which is not only significant, it's really significant, and that is our effect size, eta squared of 0.155, which means we're explaining about 15.5% of the variance. Holy cow! It works! Yay! We win the statistical game. Well, it's actually a little more complicated than that. So let's go ahead and dig a little bit deeper. So step 1, again following the 8 steps data analysis. Step 1 is we state a strong theoretical hypothesis and decision criteria. So earlier I said among heroin users, those who report having more healthy behaviors will report less psychological distress after controlling for mental illness. So that's kind of a statement, and we might say that, or we might, at least for ourselves, say distress is equal to B0 plus B1 times mental illness plus B2 times health. And like I said, we need to map theory to data, and one of the ways we do that is by identifying the specific parameter that is of interest. And so in this case, that is B2. That is the parameter of interest here. So how much does health influence distress once we control for mental illness? And that is exactly what B2 tells us. So here is an example of a strong hypothesis. We could say we predict a standardized difference, or Cohen's d, between the highest health rating, very good, versus the lowest, which is poor, to be at least d is equal to 0.3. And we might follow that up with saying if it's weaker than 0.3, we do not consider it to be clinically relevant. And so note, my camera sure likes to stop recording. Back to the video. All right. So, so linear models assume that the residuals are normally distributed. We'll talk more about what that means once we get to the univariate class. And if you look at psychological distress, which is the dependent variable, and the residuals are created from the dependent variable, we obviously got problems. And one of the biggest problems that I see is that the mode of the data set is at 0. Most people have no psychological distress in the data set. Well, that's a problem. And also, if you look at probability of mental illness, likewise, the mode is at 0. And in my experience, anytime you have an independent variable and a dependent variable who have modes at 0, you tend to have issues with nonlinearity. So step 4, we plot a graphic to match the analysis. And so for this analysis, the appropriate graphic, or the appropriate analysis would be an ANCOVA. And a graphic that matches an ANCOVA looks at like the ones on the right. And what I have done here is I have shown lowest lines rather than linear regression lines, because I want to see if the data tend to bend. Because one of the assumptions of statistics is you can fit a straight line between the x and the y variable. Well, clearly that ain't happening here. We got all sorts of bendiness going on. And so this tells us that ANCOVA would probably be the wrong type of analysis to use. But let's go ahead and look at the residuals just in case. And again, this is a preview to the univariate class, but residuals give us a better idea of whether we have violated the assumptions of the model. So step 5 on the left is a residual dependence plot, and basically what you're looking for is if there's any sort of relationship going on, that's a problem. Now normally when you look at a scatter plot you want to see a relationship, but with a residual dependence plot you do not want to see a relationship. And so there's clearly some nonlinearity going on. We also, at the right, is the histogram of the residuals. And they're not bad, but they don't look terribly normally distributed. And so at this point, this ought to be a wake-up call for us that the standard way of approaching data analysis doesn't make sense. So we have several alternatives. We could transform the data. We can use non-parametric procedures. We can use robust methods that utilize trimmed means and Winsorized variances and that sort of thing. Or we could use generalized linear models. And at this point, given that our model failed, it is best to consider ourselves in exploratory mode, or as Tukey called it, rough confirmatory mode. And so at this point, p-values don't even make sense anyway, because we're making all sorts of adjustments. So now, at this point, now that we know that our model failed, we have to go back to step 4 and plot different graphics that map onto the different types of models that we're going to audition now. And so for this analysis, I decided to try an ordered logistic model, which is visually represented at the top, and a non-parametric model at the bottom, which basically uses medians and more robust methods of calculating variances at the bottom. And so if you were to just look at the plots, and basically when I look at a plot and when I look at the fit, I'm asking myself, does the line tend to go through the densest part of the data? And for the ordered logistic regression, for the most part, that seems to be the case. And likewise for the non-parametric model, the dot in the center is the median, and they tend to be right in the center of the data, as you would expect. Now back to our substantive question. Does health seem to make a difference in psychological distress? So can you somehow mitigate psychological distress by promoting good health behaviors? And according to this data set, it doesn't seem to be making that much of a difference. If you compare the fit of the model for those who are, for example, very good and have a 50% probability of mental illness, it looks very similar to those who are good, and poor is a little bit higher, but really not that much higher. So there may be trivial differences, but they're not massive. And likewise for the bottom, you got fair, good, and very good. Those medians look almost identical. So now we can move on to step 5 and study the parameter estimates and the effect sizes. And so like I said, I have 2 models here. One is a non-parametric model, and one is the ordered logistic model. And so here are different parameter estimates or effect sizes or measures that we might find meaningful. And so for the non-parametric model, the median predicted value on distress is 7 for fair health, 6.5 for good health, and 6 for very good health. So if we were to bootstrap that confidence interval, the difference between fair and very good is between -7.5 and 2. Well, that's quite a range. And so the maximal difference between the very highest health condition and the very lowest health condition, well, by the way, I aggregated things just because of small sample sizes, but still, between the top and the bottom, you're only a 1-point difference. And when the scale goes from 0 to 24, I think it is, a 1-point difference isn't all that impressive. And now for the ordered logistic regression model, when I'm doing ordered logistic or any sort of generalized linear model where interpreting the parameters is much more difficult because you tend to take odds ratios or log of odds ratios or something like that. And so they're harder to interpret. So what I tend to do is I tend to anchor the predictions in specific areas. So let's say your probability of mental illness is at 50%. Now let's say you have somebody who has fair health and very good health. Well, you have a difference of 4 points. And on a 24-point scale, it's okay, I guess, but it's not terribly impressive. Whereas for a 25% probability of mental illness, you got 12 for both. So how much of an effect does health have? It's not all that impressive. So step 7, we make a decision. Now remember our original decision was we would consider it clinically relevant if D, the Cohen's D, between the highest and the lowest group exceeded 0.3. Well, D isn't really a relevant metric anymore because we're not even doing non-parametric, or because we are doing non-parametric stuff. And so Cohen's D assumes a normal distribution because you're computing means, which are sensitive to skewness, and you're computing standard deviations, which are sensitive to skewness. And so it doesn't actually make sense to use D anymore. And so if we were to decide to further pursue this in a replication set, we would probably set new decision criteria based on more non-parametric metrics. So step 8, repeat with new data, which I don't have, but that would be the next step. Or at this point, you might say, well, it's actually not worth pursuing because the effect size was so tiny. So let's go ahead and compare the conclusions that we gleaned from both of them. Now, if we were to use standard NHST language, we would say self-reported health rating was significantly associated with psychological distress, and we'd report this very impressive p-value and a respectable effect size, and we'd feel pretty good about it. But that would be very misleading and a very inaccurate picture of what is actually going on. Whereas if you were to look at the right plot, that shows a much more accurate representation of what is going on, and it seems to indicate that health ain't doing much. So, conclusions from this: NHST is inadequate, so reducing the richness of our data to a single p-value is very much like eating a single sprinkle off of a birthday cake. What a shame indeed! So much richness remains in our data. And the 8 steps is an alternative to NHST. It integrates theory and data analysis. It places decision-making back in the hands of the researcher, as well as the scientific community where it belongs. You might say that p-values have hijacked decision-making from applied researchers. Well, let's go ahead and put it back into the hands of the scientific community where it belongs. And in addition to that, it is graphically focused, which prevents making embarrassing errors. And it invites researchers to think in terms of estimation, and it also invites researchers to be a little more cautious about their conclusions. And finally, it invites a deeper understanding of one's data. So that wraps up our discussion of statistical conclusions, validity. Again, statistical conclusion, just in summary, statistical conclusions validity is concerned with the inferences we make about rejecting the null or failing to reject the null. And what I'm advocating here is that we should probably become far less concerned about the null hypothesis. And by the way, if you follow the 8 steps, it's impossible to make a type 1 error because you're not making any decisions about the null or the alternative. Now granted, you could make a false conclusion based on your decision criteria, but you're going to be a whole lot less likely to do that following the 8 steps because you got graphical representations and it's inviting you to think about the uncertainty associated with the data. So that's statistical conclusions validity. We also talked about internal validity, which is concerned with whether the causal inferences we make based on our research are appropriate, or are there confounds at play. And like I said, the best defense against threats to internal validity is random assignment to treatment versus control groups. So with that, let's go ahead and thank our very special guest, Professor Hawk McLagan. That's his name. Aye, thank you. It's been a pleasure to be with you all. Awesome. And we will see you later.